Good morning, or good afternoon, or good evening, depending on where you are in the world. We have people attending from all over. My name is Shari Kraber, and I am one of the consultants at StatEase Incorporated. We reside in Minneapolis, Minnesota, in the United States, and I'm very happy to have you with me today. I'm going to be keeping everyone muted, as that helps facilitate less feedback sounds. If you have questions during the webinar, feel free to type them into the question box that's on your screen, and I will get to them as I can. The most effective way of getting some good questions answered is to follow up with me via email to stathelp@statease.com, and I will get to those questions immediately following the webinar. And then we can talk about more of your specific situations, specific questions. So I am here today to give some thoughts about some tools that you can use when you have different ways of doing DOEs. A few different techniques we're going to be talking about today. We're going to be talking about a foldover technique and one factor at a time studies augmented into central composite, and we'll also talk about central composite designs augmented into optimal designs. The last technique that I'm talking about, the optimal into further optimal augmentation, is one that can also be used with mixture designs. And I had that question come up at the last webinar I gave, so I thought I'll throw that in there. So we're going to spend the first half of this talk talking about a couple of different foldover methods and kind of pros and cons on the foldover method. It's a classical technique that can be used to augment a design. So let's see what it's all about. A foldover is when we take the design that we've currently run and we've added the opposite runs to it. Usually it's the other half of the design. So if you see the initial 4 runs that I have laid out in the upper left-hand corner of the screen, I have 3 factors, and I basically just set up a half fraction design, 3 factors on 4 runs. Now this is obviously too small of a design to run normally, but I'm just using it to illustrate what the concept of a foldover is. You can see that factor A varies from -1 to +1 to -1 to +1 as we go through the runs. When we do the foldover, we do the opposite set. So now A is going to vary from +1, -1, +1, -1. And likewise with B and with C, you can see that we have done all the -1 settings, the low-level settings, and in the second half of the design, we would do all the +1 settings. Now the nice thing about a complete foldover of the design is that this changes the resolution 3 design into a resolution 4 design, or possibly even higher. This means that we decouple those main effects from the 2-factor interactions. I am assuming, as was stated in the description, that everyone coming in does have a bit of understanding about fractional factorial designs and alias structures. I have a few slides that are a little bit more on the advanced side of the aliasing that I'll show for those of you who get rather excited about that math. So we'll, if you don't have that background, then you might want to go back to some of the other webinars we've given in the past. So we can take a resolution 3 design and fold it over and get a resolution 4 design. As I'm going to talk about shortly, resolution 4 designs, if we do the complete fold over on them, they can sometimes run into problems. So we'll talk about that in a minute. We're going to start by looking at a really classic design, which is 7 factors and 8 runs. It's a resolution 3 design. I would not normally recommend this for a screening design because all the main effects are going to be aliased with or confused with the two-factor interactions. So if there's a two-factor interaction present in this design, it is guaranteed that it will give you the wrong answer because it will be identifying that as a main effect and therefore probably be misleading. But the situation where this might be an acceptable type of design to run is a possible verification or validation test that has to be done very frequently, especially in the world that's regulated by the FDA. They may have to do a verification study at the end of a long series of DOEs. So this would then be an acceptable choice. Our main effects are still aliased with the two-factor interactions. So if we use this design, the particular scenario that I'm looking at actually ends up showing that factor A is statistically significant. An aside on this webinar also, I will not be going through analysis details of these designs. I'm focused very much on the design and how to augment the design. The analysis details are also given in other webinars. But this design has factor A significant. Now, looking at the aliasing for factor A is completely aliased with 3 other two-factor interactions because we can only estimate 7 unique things in 8 runs. So A is aliased with the BD interaction and the CE interaction and the FG interaction. If you are completely comfortable that none of the interactions in this whole design are significant, then maybe you can go ahead and assume that A is the correct answer. And if you have the subject matter knowledge to make that assumption, then that's great. But if you do not, if you look at these interactions and use your subject matter knowledge and say, some of these could possibly be real, then you need to do additional work and additional runs to figure out if it really is the main effect or if it might be one of the interactions. So we can augment this original Resolution 3 design to separate factor A from the two-factor interactions it's aliased with. We do that using this complete foldover, which, as I said, gives you a new block of runs. It's going to give you the same number of runs as you originally had. So we started with 8 runs, so we're going to create a new block of an additional 8 runs with the factor levels at the opposite settings of the original design. We're going to change all the signs. And as I mentioned with Resolution 3 designs, this is going to separate the main effects from the two-factor interactions, giving us a Resolution 4 design. And this, I forgot to mention, this presentation can be downloaded from our website. And so if you want to do that after I'm done talking, then I've put the procedure in here so that you can go back and check out how to do the foldover in Design Expert software. You first of all always have to make sure that you are on the design layout screen, the spreadsheet. Any type of augmentation has to be done from that spreadsheet view. Then you go up to the Design Tools menu, click on Augment Design, Augment, and we're going to choose Foldover in this case, and then you will get to this screen where we are going to do the complete foldover. So you can see there's check marks by all of the factors, and then we'll click OK, and the additional 8 runs will be added to the design. This screen is showing you the original 8 runs in block 1, and the second block, block 2, is showing the augmented, the folded over additional 8 runs. We always put that augmentation into a new block so that if there are any time-based effects, they would get removed from the analysis, and so you have a little bit cleaner analysis. Now, Here's a little bit of that extra math I was talking about. So if you are familiar with how fractional factorials are built up, they are always based on something called the defining relation. And for a resolution 3 design, you're going to have a defining relation that looks something like this, where I, the identity column, equals ABD and ACE and BCDE, etc. You can see that the shortest words in here are 3 letters long, ABD, ACE, and there's a couple others. This means that this is a resolution 3 design. That's how we define a resolution. It's the number of letters in the shortest word. When we add block 2, and we are adding the opposite signs of block 2, the defining relationship for the second block all by itself ends up being a minus ABD and a minus ACE, etc. All of the odd length words in here get minus signs added to them. All of the even length words, we cancel out the minus sign, so they become a plus. Now we have to evaluate the 2 blocks put together, and we add these 2 systems. So if you take ABD and add a minus ABD, that will cancel out. And likewise, for all the 3-letter words, you can see that they all cancel out. So the defining relationship of the 2 blocks put together is now one that consists of just 4-letter words, giving us a resolution 4 design. And this separates then the main effects from the 2-factor interactions. Sorry. At the end of this particular problem, the final result was that factor A was really the culprit, and the chemist decided what was going on physically. There was not a 2-factor interaction, and so they could deal with the issue of reusing their reagent. That was the issue. So anyway, that's kind of beside the point of this particular webinar. So what happens if we have a resolution 4 design? That's where I'm going to go next. This resolution 4 design would be good for screening. In this case, we have 6 factors, and a resolution 4 design for 6 factors is going to be a total of 16 runs. So we could set this up in Design Expert, the 6-factor, 16-run design. We have some numeric factors and some categoric factors in here. The 16-run design has an alias structure that looks like this. You can see the main effects are aliased with 3-factor interactions. We generally consider that an acceptable situation, and we say that we can correctly identify all of the main effects. The 2-factor interactions, however, are aliased with each other, and so it's going to be a little bit more problematic to figure out which is the correct 2-factor interaction if something does come up statistically significant. So let's see how this problem develops. The half-normal plot that we get of the effects shows that we have 4 significant main effects, A, B, C, and E, and we also have a 2-factor interaction. Okay, because we know that the main effects are basically clear of any other 2-factor interactions, we know that these main effects are correct. The question becomes, is this the correct 2-factor interaction? This is the AB interaction. Let's see, let's go back and see what AB was aliased with. So looking back at the alias structure, I can see that AB is aliased with CE. So does that cause us a problem here? Well, let's see. I have the parent terms A, B in the model. I also have the parent terms C and E in the model. So is this really the A-B interaction, or is it the C-E interaction, or is it both? This is the dilemma that we get into when we run fractional factorial designs. Sometimes your subject matter knowledge can help you determine which is the more likely interaction, and sometimes you just have to do more work. Let's explore the idea of this being the A-B interaction. You can see the polynomial model on the right side and the interaction graph on the left. And this is the picture. What do you guys think? If we were to substitute CE in for the A-B interaction, if we were to substitute CE, what would the graph of CE look like? Just think about that for a minute. I don't know if you've found it yet, but there is a nice little feature in Design Expert on the half normal plot. If you have a fractional factorial design, you can simply right-click on the factor and you will pull up the list of aliases. You can then actually relabel right there on the graph. You can redefine what that term is. So I can switch it from AB to CE very simply. Of course, you can also go to the alias list and switch it there, but switching it right on the graph is convenient. So we've switched it to CE, and here's the CE graph. It looks different. The polynomial model has stayed the same. These are the exact same coefficients. You look at this: 71, 46, 33, 80. I'll go back 2 slides. 71, 46, 33, 80. The polynomial stays the same. What changes? The change is the label, the CE label. Why does that affect this graph? Well, because this correction, this minus 80 correction, is now applied to the C coefficient and the E parent term, rather than getting applied to the A and B parent terms, where we are applying this correction to a different set of terms. So the graphic for C and E is actually very different than the graphic for the A-B interaction. When I teach this in live classes, I always sense that this is a bit of an eye-opening experience for people, and hopefully you're seeing the same thing, that you can't assume that because things are aliased, that means they're the same. The end results will not be the same. As a matter of fact, if we were trying to minimize this particular response and we use the model with the A-B interaction live, factor B would end up being set at its low level, and factor C would be set up at its low level to get the minimal thickness. Alternatively, if we use the model with the CE interaction, then both B and C end up being set to their high levels. How do we set up the process if we don't know which model is the correct one? In this case, subject matter knowledge is simply not going to do, because either of these could be correct. So we're forced into the situation where we really do have to augment this design and decouple the A-B and the CE interactions. Okay, so we can fold over this design. Now, this particular Resolution 4 design, if we did the complete fold over of it, it actually generates, when we do what we think are the opposite runs, the complete design ends up being a replicate of the original design. This happens with certain of the Resolution 4 designs. It does not happen with all of them, but it does happen with certain ones. And I have certainly had clients who have had a surprise that happened, and they had gone ahead and run the additional 16 runs and then discovered afterwards that their aliasing was exactly the same. They hadn't done anything new, and they were a little disgruntled to realize that they had done all that work for nothing. Somebody did pop in a question, why not just test both possible solutions and see which one is most correct? Totally agree. From an engineering standpoint, that's the simpler way, but that doesn't help me complete my webinar. So for today, I'm going to show you how to do the foldover to get the statistically best solution. All right, so we're going to fold over on a single factor, and this is going to free that factor and all factors involving that particular one from aliasing with other main effects and two-factor interactions. Again, we're going to go to the spreadsheet view, click on Design Tools menu, and we will augment. When we get to the foldover screen, we will actually follow the guideline. It says right at the top of the screen, for Resolution 4 design, select a single factor. We're going to fold over on one of the significant factors. It would not matter if you chose A, B, C, or E. We can choose any one of those four factors to fold over on, and it would give us the same result or equivalent results. So we're going to choose A because it's the first in the alphabet, and we just like to do it that way. All right, so back to some math. What are we doing here? The defining relation for the first 16 runs is the identity equals ABCE and ADEF and BCDF. So there are 3 words with 4 letters each. Again, that's a Resolution 4 design. When we fold over just a single factor, that's the only factor that becomes the opposite. So just folding over on factor A, in the second block, we're going to have a minus A. So down the relation for the block 2 is a minus A BCE, minus A DEF, and the BCDF. So combining those 2 blocks together, analyzing them together, any of the words that have A in it drop out, and the final defining relation doesn't include factor A. That means A is going to be clear of aliasing. Also, the interactions with A are clear of aliasing. So AB, AC, AD, any of those 2-factor interactions. So that's kind of neat. This screen is showing the original, the first half of the runs, and the original alias structure. You can see where we had all of our 2-factor interactions confused with each other. After completing the foldover, you can see A is clear, and the interactions with A are now only aliased with 4-factor or higher order interactions. So let's see, our problem area was AB and CE were aliased with each other. And you can see that they are now completely split apart and can be estimated completely independently from each other. All right, so the scientists can go back and do these additional 16 runs, and they will get the correct answer, figuring out if A, B, or C, D is correct. Now, realize they have to do another 16 runs. That's a lot of work, right? So what if we had the ability to get by with doing half of that? That is where the semi-fold method comes in. The semi-fold method allows us to do only half of the runs. So we can do 8 runs rather than 16 runs. when we fold over, the complete foldover or a single factor foldover, the number of additional two-factor interactions that can be estimated beyond the original design is usually less than half the number of runs in the folded over fraction. Okay. If your goal is to estimate additional two-factor interactions and to increase power, then foldover is a good choice. It's great. You need the additional runs to increase your power. If you are only trying to decouple these extra two-factor interactions, then the full foldover is not efficient. A semi-foldover would allow estimating just as many two-factor interactions. So, what's the semi-fold? What we do is we split the fraction into two groups, and only one of the groups is run. And so the number of new runs are actually half of the original design. So we start with the same process as we do with the single factor foldover. We pick that single factor. Here we're going to use A. Then we also pick a factor that's not involved in the interactions that we want to separate to do our split. So that's key. Your first factor that you choose is a factor that's significant, that's in one of the interactions. The second factor that you choose is one that's not involved in the interactions. So in our case, we could just take that last factor, factor F. It's actually an exhaust cover. The cover is either kept on the system or removed from the system, so it's an on or off. We would rather keep the cover on than leave it off. Leaving it off just makes it kind of messy. So we are going to keep the F plus side and not run the F minus side, and that's on this next screen. Again, I put the instructions if you want to go through this in Design Expert up here. When you choose the semi-fold option, you get this screen with a lot of, we tried to write a lot of explanation on here to guide you along. Choose the factor to fold on, that's factor A. Then secondarily, choose the factor and the level to retain. So the second one is choosing an insignificant factor and tell it which half of the runs you want to run. The other half will be discarded. All right, so the full fold is on the right side here, and if you remember, we had been able to estimate all the two-factor interactions that had A in it, and then some of the other interactions are still aliased together. If we just did 8 runs rather than 16 runs and used the semi-fold method, then look at the results. It is nearly the same. The two-factor interactions are aliased with three-factor interactions, but if you assume that those are negligible, then they can be ignored. The aliasing with the other factors remains the same. And CE, again, is aliased with some three-factor interactions. But basically, this gives you the same results at half the price. Now again, remembering the full foldover would have given you more power, but assuming that we don't need power, then the semi-fold gives you the same quality of information as far as terms that you can estimate. So definitely a very good option I would choose, and I'm betting that probably nobody out there has tried this yet. So next time you're in this situation, it's definitely a tool you should consider. All right, so let's summarize the foldover methods, and then we'll move on to a couple of the other topics. So the complete foldover, you change all the signs on all the original runs with the resolution 3 designs. We separate the main effects from the two-factor interactions, producing a resolution 4 design. And with resolution 4 designs, you might get a replicate. So that's the danger area, which is why we have that warning in Design Expert for you to actually do a single factor foldover. Just change signs on only one factor. For both Res 3 and Resolution 4 designs, That will de-alias the foldover factor and all its two-factor interactions. Okay, and the third option is the semi-fold. Just do half of the extra runs, and this usually allows estimating as many two-factor interactions as the foldover would. Note that this is just applicable to Resolution 4 designs. The semi-fold will not work for the Resolution 3 designs. I strongly advise checking your design evaluation, checking the aliasing after you do a foldover and before you actually physically do the work. Make sure that whatever augmentation you have done is actually giving you the results that you expect. You'd hate to have a surprise like that one client did when he did all the work and then discovered they had just done a replicate of the original work. The other option, of course, is to choose a higher resolution design in the first place, and Design Expert has other designs other than these kind of classic textbook designs. We have other designs that might be considered the optimal designs. The minimum run Resolution 5 designs, they're characterization designs, and we also have the other screening designs too, so definitely things to try. In this particular case, for 6 factors, the minimum run Resolution 5 design is actually only 22 runs. So for that 22 runs, we could have estimated all our main effects and all the two-factor interactions. Even with the semi-fold option, we were at 24 runs. We did not have all the two-factor interactions yet. So if you plan ahead and just run a little bit higher resolution design to begin with, you might be surprised at what you can get. So again, explore the different design options before you physically run your design. There are a lot of them available to you, and it doesn't take that long to explore these. Certainly that time is well worth the effort. All right, I'm going to switch gears here a little bit, and we're going to talk about your colleagues who still haven't quite bought into the whole concept of running designed experiments. Perhaps they are still running one factor at a time systems. People are always asking us, can we save this data? Can we reuse this data and turn it into a designed experiment? Well, I didn't invent this. This concept was actually brought up at a conference about 2 years ago, and I was really intrigued by this, and I thought this might be a way of drawing people into DOE who are kind of resistant to it. So I'm going to take the scenario. Let's just say that your standard operating conditions are okay, but you want to test in the nearby area and see if you can find a little bit more optimal condition. So we look at our factors and we run them a little bit higher and a little bit lower from our standard settings. This is done all the time in labs and out on the production floor. We're just kind of doing a little bit of one factor at a time, exploring. Okay, so you have the data. What happens if I take factor A and increase it higher? What happens if I decrease it? What happens if I take factor B and set it lower or higher? If you have that data, these form the axes of the central composite design. Now, why don't we fill that out and add the corners to this? If we do those additional runs, add the corners to the box, we will complete a face-centered central composite design. We reuse the existing data and just fill it out, augment it with the extra runs that are needed. That's kind of a cool idea. So I've taken an example. The statistical or the scientific details here aren't important, but you can read it if you download the presentation that I have on our website. So this face-centered central composite design, I'm just kind of showing on the next page how we can split it apart. So I built this face-centered central composite, and what I did was I ordered it into the axial points first and the factorial points second. So I can have my people who run the process start by exploring factor A, the nozzle rate. And the first thing they're going to do is, going off of their center point, they're going to take nozzle rate a little bit lower, down to 300, and a little bit higher, down to up to 500. Note that everything else is set simply constant at its center point. Then in the next stage, they will take factor 2, going a little bit lower and a little bit higher. Note that factor A was set at its center point, and so as factor C and factor D, and so on. So you can see that we're progressing through the 4 factors. Each time we get to a factor, we just explore a little bit lower and a little bit higher. Now, this is not a designed experiment. You cannot get a good statistical analysis out of it. But you can do a visual inspection of the data and see if there are any promising leads. And so we were trying to minimize our growth response here, and anything below a 1 is actually a good result. And so I can see, yes, I have definitely some places in the system where I'm getting some good growth rates, some minimal growth rates. And so this proves that there is some positive somewhere in the system. I'm not sure if there are interactions yet. I can't tell. But I have evidence to say that it's worth it for us to keep exploring in this area. So with that, perhaps I can convince the powers that be to let me finish this out, do the entire factorial design, and augment that first set of axial runs with the additional factorial points. I would also note that you would want to do a few more center points. I would hope that you would randomize all of this and do a couple of center points so that you can tie these 2 blocks of information together again. From a statistical standpoint, that's a good idea. Here is just a graph of what we discover at the end of this particular study. The actually optimal conditions are not at the center. They are not at the corners of the cube. They're kind of at an intermediate zone. So you can see them in this darkest blue area. We were trying to minimize the growth rate here. And so this darkest blue is actually our optimum area. We would not have found this area doing 1 factor at a time movement. We needed to understand that there's an interaction between the A and the D factors, and we needed to get that picture of where the best settings were. Okay, so summarizing this little theory, stage 1, you can do the 1 factor at a time study, starting with the axial points, and you can use existing data. That's neat. Well, we don't have to discard that. Inspect the results for evidence of potentially good results, and we're not going to do a statistical analysis. If there are some potentially good results there, then expand this by adding the factorial corner points, complete out, finalize that RSM analysis, and do your optimization. All right, one last topic today. What if we have a standard response surface like a central composite design or a box Benken design, and the analysis is just not going as well as you had hoped? It's not fitting that standard quadratic model very well. This technique can also be used for mixture designs. So the little design that I'm using is a two-factor central composite design with temperature and stir rate. And here's the data. We have our normal combination of center points, axial points, factorial points. When we do the analysis, we get a fit summary that looks like this. Looking at the linear model first, we can see that the p-value is not significant, and the lack of fit is highly significant. In addition, your R-squared values are extremely poor. Negative predicted R-squared means that you can interpret it as meaning that you could simply use the overall mean of all the data, the average of all the data, use that to predict the entire design space, and that prediction would be more accurate for the design space than the linear model. That means it's a very, very poor model, and we wouldn't want to use any model that has a negative predicted R-squared. The same situation with the two-factor interaction model. That's also a poor fit, poor predictions. The quadratic model is the suggested one by the software, by Design Expert. At least it has a somewhat significant p-value. However, the lack of fit is still not significant. R-squared is getting a little bit higher, but the predicted R-squared is still very, very low. I wouldn't use this for making predictions. Maybe you can use it to simply explore the design space a little bit here. It's going to give you some information, just not very strong information. What is popping up on my radar here is that my cubic model actually is highly significant and takes care of the lack of fit. Now lack of fit is not significant. That's good. That's very positive. And the adjusted R-squared and predicted R-squareds are high. So why can't I just fit a cubic model right now? Because it's aliased. The aliasing means, as we've just kind of reviewed, that we are not independently estimating all of the terms in the cubic model. What we're doing is we're combining the cubic terms together and testing them as a group. As a group, there is significance, and as the best cubic model that we can fit, that seems to be explaining things. But we actually cannot use the cubic model just yet. We don't have enough runs to independently estimate all the terms. But this tells me that, hey, it would probably be worth my while to add the extra terms and try to fit that. Here's the picture of how the quadratic model is fitting the terms and fitting the data points. And you can see that on the back side, our design points are up high, like this slope should be coming up higher on the back, and maybe it needs to be dipping down more in the front. It's just not fitting all those points very well. So the standard RSM designs, like the central composite and the box Benken, they were originally developed to fit quadratic models. They're optimal for fitting quadratic models, and so many systems work really well in that quadratic model polynomial. If you have a system that indicates you need to go beyond that, we're going to have to augment it. We need to run at least one additional run for each aliased coefficient, plus an extra run to make that block correction. If you remember, Design Expert's going to put the new runs in a second block, and so you need to account for that block also. Now, Design Expert is going to default to 2 runs per coefficient. You can modify that if it ends up giving you way too many runs, but that is the default, and it works well in a situation like this where we only have a few runs. So first of all, looking at the design evaluation for this central composite design, for a cubic model, you can see that those cubic terms, the A cubed term, are aliased with the linear terms. The B cubed term aliased with the linear B term. Also, those cubed terms are aliased with some of the other cubic terms. So A squared B and AB squared. So we really need to split apart these two terms, the A cubed and B cubed, and also we need to estimate the block term. So at least 3 runs are needed, and we're actually going to default to 6. So we use our standard method, go up to the design tools, go to augment design, augment. This time we're going to choose the RSM optimal augmentation. And what trips people up sometimes in getting to the screen is they don't realize that you have to edit this, you have to edit the model. It will tell you which model you're on currently. So it tells you what you can currently fit. You need to change that to what you want to fit. So in this case, I clicked on the Edit Model button and I changed it to a cubic model. That tells me that I have 3 required model points. I have 3 additional model points for a total of 6 new runs. You can optimally add in maybe some center points if you'd like. If you have more factors in the design, then this may be a lot more runs. Maybe you're at 12 more runs, and so adding the additional model points of another 12, maybe that's too many for you. You can certainly decrease that additional model points a little bit if you need to. Here are the additional 6 runs, and we can physically do these and then fit the final model, and we get these wonderful cubic pictures that our marketing department loves to show on our marketing materials because they're just fun to look at. Well, we get these swooshes and all sorts of interesting patterns. So you can see that we are fitting these corner points much better now, and our optimal conditions were up here at this 40-degree temperature, so we really did want to get good fit in this area. So that rounds out this particular example. And as I said, you can do this with mixture designs as well. So when we do the central composite design to an optimal cubic design, we start by running that standard central composite. We fit up to a quadratic polynomial. If none of the lower level polynomials fit well, and there has to be evidence that a cubic model might fit, then we can augment with the optimal augmentation and do the extra runs. You want to look for that significant p-value, insignificant lack of fit, and the higher r-squared values to really justify the additional work that you could do. The other option, of course, is to constrain your area of interest and say, you know, I don't care if I fit way out at the corners, I'm just concerned about the fit at the interior. Sometimes you can rationalize having a model that doesn't fit quite as well at certain points. That's where those 3-dimensional graphics really come in to play nicely. You can look at them and decide how the fit is at the area you're interested in. All right, so this concludes the heart of the material that I wanted to share today. I wanted to just look at a few ways you could do DOEs differently, using the fold-over technique to augment the design, building up from a 1 factor at a time study, and augmenting designs optimally when you need to get extra information. I would definitely welcome questions from you. As I said at the beginning, using our email address, stathelp@staties.com. You can send questions right there, and I will be online now to answer those as they come in. I thank you for the time that you've spent here today, and hope you come back for some of our additional topics in the future. So with that, I thank you again for coming, and have a great day or a great evening depending on where you live. Thank you very much.